All right. Good afternoon, everyone, and welcome to another Iowa Learning Farms webinar. This week's topic is Building South Dakota's Roadmap to Water Resilience with Dr. John McMaine. If you have any questions, feel free to go ahead and submit them to me in the chat, and I'll get them to Dr. McMaine at the end of the presentation. So whenever you're ready. You are muted, John.
Thanks. It wouldn't be a Zoom meeting or a Zoom webinar if that statement wasn't said. So had to start muted, I guess, to make sure that happened. But thanks for the invitation and thanks for the introduction. It's always great to really get to talk about work that we're doing, and especially when there's so much we can learn from other states. So hopefully what we talk about today can, result in some collaborations with whoever's on the webinar today. But yeah, excited to talk about some of the work we're doing with both water quantity and water quality in South Dakota. So I would, of course, be remiss if I didn't acknowledge all the great folks helping and leading a lot of this research. So shout out to a really great team of students and staff, postdocs that are helping with this work and leading this work. And of course, really thankful for a lot of good funding opportunities we've been lucky enough to get. So I want to start with really where the rubber hits the road many times, and that's how does weather, or how do moisture extremes manifest in crop insurance. This is, it's maybe not a perfect way to look at kind of how water affects agriculture, but it's a pretty good look on a macro scale of how moisture extremes can have an impact related to agriculture. So 2019, no surprise, but in South Dakota, the number one cause for crop insurance claims, crop loss, was due to excess moisture. 2019 was an exceptional year. It was, record flooding across Nebraska, Iowa, South Dakota. And so it's no surprise that this was something that we saw. And it's a trend that we've seen actually kind of over the last decades. This year is not manifesting that trend, but this is work that Dr. Chris Hay and Dr. Dennis Toddy did when they were in South Dakota, and looking at kind of how these two different time periods have changed. So you have one time period from 1991 to 2009, comparing that to 1961 and 1990. And what they found was that there's been an increase of 2 to 5 inches in annual precipitation. And so when you think about that from a perspective of what the landscape is used to, if you will, or what the landscape has been formed under or evolved under, that can have pretty significant impacts. So in eastern South Dakota, we're looking at anywhere from 22 to 25 inches of rain, or precipitation, I should say, on average. And so you add 2 inches in any given year to 5 inches in any given year, that's a pretty significant difference. So it's anywhere from really 10 to 20% or so. And it's not just the amount, but we've also seen more intense events, both from a precipitation perspective as well as duration as well as timing. And then we've also seen changes in when it comes. So winter precipitation is projected to increase by 10 to 20%. And then we've also seen kind of a similar trend. This is, again, the work from Dr. Hay and Dr. Toddy of changes in the timing. So on the left, you see the change in fall precipitation. So especially prevalent, in that eastern South Dakota, eastern North Dakota to kind of central, that anywhere from an increase of 20 or 30% to over 60% in the fall. And then again, kind of that 20 to 30 to over 50% in the winter. And so when you think about, the amount is one piece, the timing is another piece. And so not only are we seeing challenges like what we saw in 2019, but we're also seeing challenges at the other end of the spectrum. And so 2018 was also a wet year, considered a wet year. And so no surprise, the leading cause for crop insurance claims in South Dakota was excess moisture. But number 2 on the list is drought. So you have the same state and same year, and you have 2 opposite ends of the spectrum that were driving crop loss. And so 2017, kind of a similar story, but flipped the script. So drought was the number 1 cause for crop insurance claims in 2017. So it was a relatively dry year. But again, number 2 on the list was excess moisture. And so we're seeing this trend of more water in the spring than we can use. And so that leads to kind of this water excess issue, and then not enough water in the summer when we need it. And so that leads to this drought issue. And it's not the only thing that we're dealing with. We're also dealing with flooding on the excess end of the spectrum. And then, in years like this year, we're also seeing issues with water availability in some parts. So in 2019, across the Missouri River Basin, the upper Midwest, there's almost $11 billion of damages. But then you look at townships, and so this is, small towns in South Dakota. The middle picture there is talking about Turner Township. $32 million almost of damage in South Dakota townships in 2019. When you compare a city like Sioux Falls, with a pretty robust tax base, to a township like Turner Township, a $70,000 repair, that's a pretty significant chunk of their annual operating budget. And so it's not just about agriculture at the field scale, but it's also thinking about the whole watershed and what are options we have to build resilience into the whole watershed. And so that leads me to talk about the first project that I'm going to talk about today, and that's what we've pitched as the roadmap to water resilience. Every practice counts. And so it's been a really fun project because there's been a lot of partners on this. And so it's been really, I guess, meaningful to work across kind of the agriculture conservation spectrum. Partners that don't necessarily always, traditionally, historically work together. But we've really been able to find this common ground around how do we make agricultural systems more resilient at the field scale, and how do we translate that to improve resilience at the watershed scale. And so those are essentially the 2 questions that we're trying to ask. From the soil moisture perspective is, can we use soil health practices to reduce the soil moisture risk? So what we're saying is too much or not enough in the field. And then if we do that enough, right, are we able to actually translate that to reduce flooding at the watershed scale? And just to step back a little bit and think about, how does management affect water? Well, it starts at the soil surface, right? So any precipitation that falls in the soil surface, that can do really one of 3 things. It can run off the surface, it can go into the ground surface, or it can go back to the atmosphere as evapotranspiration. And so when you think about the first step, right, getting into the soil, capturing that water initially, a lot of that comes down to the soil structure, the pore size distribution, if there's any type of crusting at the surface, and then bulk density, right? So a higher bulk density, any compaction that you have is going to prevent that water from going into the soil profile initially. And then once it's in there, how is it able to move through the soil? And so, if you have poor soil structure, if you have a lack of macropores, then it's likely not going to be able to move very quickly through the soil. And so these types of conditions, you're more likely to get waterlogging. You're more likely to have extended periods without enough air in the soil for healthy root development. And then it's, you're dealing with an issue that kind of compounds other issues like water quality issues, because now if you don't have plant growth, you also don't have fertilizers being used. And so then that's, potential for loss. But then once you have it in the soil, on the other end of the spectrum, what's our ability to hold that water? And that's a function of several things, but two that stand out. One is bulk density. So again, how compacted that soil is, and the other is organic matter. And so if we have systems, or if we have practices that are able to reduce the bulk density and increase the organic matter, then in theory, we've made our sponge bigger, right? We've added capacity to our sponge so it can hold more water. And then when we think about these wet springs, is there anything we could have done either in the fall or in the early spring to cycle more of that water back to the atmosphere? And so that's comes into play with crop type, right? So obviously different crops are going to use different amounts of water. If we have any types of diverse rotations, then if we have any cover crops, that we're able to use some of that excess in the fall. And that's a little bit of a unknown, right? Because what conditions we have in the fall may not translate to conditions that we're seeing in the spring, but it may also give us a ability to push that a little bit one way or the other. And so I'm going to spend some time talking about a plot scale project that's a companion project to the Willow Creek watershed, the roadmap to water resilience. And then I'll spend some more time talking about the watershed project. But for the plot scale project, it's basically looking at tillage, so conventional till, no-till, crop rotation, 2, 3, and 4 year crop rotations, and then plus and minus cover crops and plus and minus tile drainage. And tillage and rotation, that's been in that system since 1991, the cover crops since 2014, and in 2017 those plots were drained. Basically, I'll be presenting the soils information today. And then we'll talk about kind of implications that has for the watershed scale project. But we've collected cores in 2020 and 2021, and then also this spring as well. But so yeah, pretty standard, use a Giddings probe, go down to 90 centimeters for our later soil sample collections, and then split those into 0 to 10, 10 to 20, 20 to 30, 30 to 60, and 60 to 90 centimeters. And then did all the physical property analysis in-house, and then sent the samples to Ward Labs in Kearney, Nebraska for all the chemical and biological analysis. And so I'm just going to jump to some quick results. So from an organic matter perspective, which again, that was something we talked about, which affects the water holding capacity as well as the soil structure. We did see significant differences related to no-till. So no-till had significantly higher organic matter, but the interesting thing is where this actually manifested was not in that top 20 centimeters, but it was actually 20 to 30 centimeters and then 30 to 60 centimeters. So I don't know, the big takeaways from this, but it was interesting that we saw not necessarily differences at the soil surface, but it was actually deeper in the soil profile where we saw those differences. So maybe getting a little bit further down to the root zone, maybe even past that a little bit. From aggregate stability perspective, so this is in essence looking at the likelihood of that soil to erode by water. So if it's a higher aggregate stability, it means it's less likely to erode because the aggregates are able to hold together more. They're more stable. And so again, we saw differences here But from a statistical perspective, the only difference within the soil profile was in that top 0 to 10 centimeters. So when we think about, tillage or no-till and cover crops, a lot of times we're looking at the soil cover as kind of what's reducing the erosion, but this points to structure as a significant part of reducing erosion as well, because those aggregates are holding together better. What about on crop rotation? So these two figures are looking at bulk density and then organic matter. So an interesting thing from a bulk density perspective is our 2-year rotation, which is just corn and soybeans, actually had the highest bulk density, and actually our 3-year rotation had the lowest bulk density, so it was lower than the 4-year rotation. From an organic matter perspective, interestingly, the 2-year rotation actually had a higher organic matter than either the 3 or the 4-year rotation. So oftentimes we think of, more diverse rotations as leading to higher organic matter and kind of healthier soils, if you will. And organic matter is just one measure of, soil health. But we saw that the corn soybean rotation had a higher organic matter, again, manifesting at the lower end of that soil profile. And kind of our working hypothesis on this is related to the fact that the 2-year rotation, corn was a more dominant, it was 50% of the time, whereas in the 3-year and the 4-year, corn was only either 33% of the time or 25% of the time, and corn creates a lot of biomass, and so that's a lot of organic matter that's being produced, and so that could potentially be added to the soil profile. So from a cover crop perspective, really the only interesting takeaway here that I'm presenting is related to bulk density. So bulk density in our samples, we actually found a higher bulk density in cover crops as compared to no cover crops. And this is not what we expected, not really what you would want to see, right? If you're thinking about cover crop use from a soil health perspective. And again, bulk density is just one aspect of that. But kind of our working hypothesis on this is several of the years that the cover crops were used, the growing season was really challenging for cover crops. So it might have been a wet fall, might have been a really cold fall. And so there wasn't a lot of biomass that was produced from the cover crops, but you had extra passes through the field to plant and then to burn down those cover crops. And so you potentially had some of maybe the risks of the cover crops without the benefits, just because there wasn't enough growing period window for them to really get established and take off and produce that biomass, produce that root structure that we would hope to see from a really good, healthy cover crop stand. And then from the drainage perspective, I guess the big takeaway here was there was not any difference in any of the parameters that we measured on the physical side. There were some on the chemical side, which I'm not presenting today. But the working hypothesis here is that we're not in it's not a really poor drained soil to start with. So in the really wet years, the drainage would likely show some differences there, but in kind of the average years, it's not likely that we would see a lot of difference anyways. So from the results that we had, there was no difference because of drainage. So that's kind of a picture of what the types of work we're doing at the plot scale and then at the field scale as well. And so again, how do conservation practices reduce soil moisture risk in the field? Well, a lot of it starts with those physical characteristics. But then again, how does that translate to flood reduction or resilience at the watershed scale? And so now I'm going to kind of transition back and talk about our watershed scale project. And so we're taking a lot of the same types of measurements. We're doing soil moisture at several fields throughout the watershed. And this is the watershed map. It's just northwest of Sioux Falls. On the left is an actual figure that represents the watershed, the snow-capped peaks. That's the Willow Creek mountain range in eastern South Dakota. Just kidding. Anyway, so that's a joke if you've ever been to eastern South Dakota. Beautiful country, rolling hills, but definitely no mountains. So a big part of this is actually directly measuring soil moisture. And so this year we have 23 fields that we have selected, and this is, in conjunction with a lot of very willing and wonderful landowners and farmers. So we're very thankful for their collaboration. But we have 2 locations in each field, and again characterizing soils at each location. So what we want to see from the soil moisture data is really when you get these big events, or any event really, what does that translate to, right? What's the capture efficiency in essence of what falls from the sky, how much goes into the soil profile, and how much is that recharged? And then when you're on the wet end of the spectrum, how long does that stay in the soil profile? Do you see any differences with cover crops or extended rotations in the spring? Do you see any differences related to the soil characteristics themselves? And so the kind of selection process for the 23 fields was we picked a similar soil in each field. So looked at the watershed, looked at the fields that the landowners had that they were willing to let us work in, and then found, every field we went to a Nora Crofton complex. And then we know that landscape position can affect soil moisture. And so we did an upslope landscape position and then a downslope landscape position. And so in essence, what we're trying to look at, from the watershed scale is if this is our baseline condition, and if each dot on there represents some amount of storage, with any given rain event, and then the arrow at the bottom represents the discharge at the watershed outlet. If we can get more storage, if we can convert 50% of the watershed to no-till and increase the organic matter, increase the infiltration, what does that translate to for the discharge at the watershed outlet? And again, if we have a high implementation, 100% of the watershed, or a really significant improvement in soil function, what does that translate to for discharge at the watershed outlet? So another way to look at it is, if on the left, this is the current baseline storage, and then if you can hold 2 inches on every acre, across the whole watershed, about 30,000 acres, well, that's about 1.5 billion gallons of water that you're holding in the landscape. So if your baseline, it's going to overflow, you're going to have discharge. And then if you have additional storage, then that's held in the soil profile. So kind of a little more on the project pieces, we, like I've talked about, we're monitoring soil moisture and then also characterizing those soils at each location. We've been modeling the kind of trying to look at, does placement matter if we're looking at conservation in the watershed? So if we're in the riparian area versus upland of that. And then we also have an ag economist on the team, Dr. Deepti Kolati here at South Dakota State University. And so she's been trying to look at the economic benefits of, if you have improved soil moisture management, what does that translate to for profit? And then if you can take that back to the practice itself, how much is no-till worth if you do a better job of managing soil moisture in essence? Then we have a wonderful social scientist on the team, Dr. Maz Gardizi. He's at Virginia Tech University. And so he and grad students have been looking at, kind of some of the classic questions of what are the barriers that exist to implementation, but also trying to get at what is a farmer's relationship with other farmers that are, maybe on the bleeding edge of conservation, the proximity, does that make any difference? If you drive by cover crops, are you more likely to implement cover crops, for example? And then also your relationship with water. So if you're next to a stream versus if you're upland, how does that affect your interest in implementing some of these practices? So, and then again, big picture, what's the impact at the watershed scale? So this is just an example of some scenarios that we ran. So if we had our baseline condition, which is the red line, the highest peak, and then if we converted some amount of landscape to, say, grassland with a good soil condition, or grassland with a medium soil condition, or hydrologic soil group, what does that translate to for peak flow? And so, no surprise, we can reduce it a fair amount. A good soil or a medium soil would reduce it 16%. A better soil would reduce it 25%. So in this condition, in this scenario, it demonstrates that you can, if you have effective implementation that effectively changes the soil and changes those properties, and you can get some effective reduction in peak flow and potentially flooding at the watershed outlet. So that's kind of the water quantity piece, but what about water quality? And I tweeted earlier that I was going to wrap, so I guess this would be the time for that. But when we think about water quality in South Dakota, nitrate is often the driving thing that's been the situation across the Midwest because of the Gulf of Mexico. So situation that we're facing is eutrophication, high nitrate concentration in the Mississippi and Atchafalaya River Basin. Eutrophication is a combination of concentration and flow to the Gulf of Mexico. Our contribution is low. You see SD top of the watershed. Our contribution is not that red. We want to keep it that way, keep our contribution at base. So we can say we came to play in this ballet to mitigate the Gulf's decay. So that's kind of what we're looking at, right? Is how do we, we're not seen as a big contributor, but what can we do to maintain that? And so tile drainage is seen a relative boom in the last 15 to 20 years. It's not traditionally thought of as, one of the big drainage states. It's the Corn Belt is moving north and west, and so there's been a lot more drainage because of that, the changing climate, changing cropping patterns. And so really, where we're at is what's the baseline, right? So any hit song, you need a good baseline under pressure, doom doom da doom da doom, right? So you need a good baseline that you can build off of, and so that's kind of what we've been trying to do. And so we have about 34 outlets that we monitor base flow for and then analyze for nitrate and orthophosphate. So, we'll have some groups that say that the water quality and tile drainage is one step away from toxic waste. And then we have other groups that say that water quality and tile drainage is, one step from holy water, right? So what is the truth, especially from a nitrate and orthophosphate perspective? And then what we kind of bigger picture on that, once we have this baseline, concentrations, flow timing, those types of things, how do other variables affect that, right? So the management, the soils, the precipitation, the weather patterns, all of those things, once we've kind of tied all that together, well, then now that allows us to both prioritize where we need to invest at the edge of the field, right? So if we know that some soils or some crops are especially prone to of loss, then now that gives us an opportunity to maybe invest in a bioreactor at the edge of the field. And there's been a lot of this research in other parts of the Midwest and kind of more historically tiled landscapes. But the difference is, South Dakota is a pretty unique, we're in the prairie pothole region. It's newly tiled. We don't have a lot of pattern tiling. It's a lot of kind of spot tiling, targeted tiling. And so really this work needs to be done for South Dakota. So we have a roadmap for water quality related to tile. So kind of some of the things we've done, basically a lot of sampling, weekly sampling when things are running. And then again, like I mentioned, trying to tie those other variables into the results. So these are just some preliminary results. This is from last year. And across the x-axis, each stack of dots is one tile outlet. And then along the y-axis is the nitrate concentration. And just a few things to point out. One is that within each outlet, there's a pretty narrow grouping. There's not a huge amount of variability for the most part. There are some, further to the right of the figure that are very spread out. And then there's some that are, between, say, 15 and 25 parts per million. But as a whole, they're more tightly grouped within each outlet than they are across outlets. And so what this has kind of led us to believe that our initial hypothesis had some merit. There's some things that seem to be driving some of this loss. It's pretty consistent from outlet or within each outlet, but from outlet to outlet, there's differences. And so that means there's something that's, adding risk to that. So just from a numbers perspective, if you look at standard deviation across outlets, about 7 parts per million is the standard deviation across outlets, but then within each outlet, it's 2.6 parts per million. Average across all samples is 12 parts per million. Whenever I've given this information before, I get asked, well, what's good, what's bad, what should we be worried about? You can point to a few different things. You can point to the drinking water standard, but then you can point to, environmentally relevant information. And so some of the work that's been done in Iowa and Illinois and other states looking at impacts to the environment, we probably need to be under that 10 parts per million many times. Then if you look at background, background concentrations in South Dakota seem to be around, between maybe 0.5 and 1.5 parts per million. So we're quite a bit higher than what we would like. But there's potential there, right? There's opportunity because some of the outlets are very low in terms of nitrate concentration. So if we think about the big picture, it's kind of my wrap up here. Agriculture management, both from the water quantity perspective as well as the water quality perspective, we have seen both the plot scale and the field scale that agriculture management definitely affects resilience. It definitely affects our impact downstream. But with that, there's an opportunity, right? Because field scale management, things that we can do in the field, they can have watershed scale impacts. Quote I really like from Dr. Jeff Strock up in Lamberton, Minnesota with the University of Minnesota. There's no silver bullets, it's only silver buckshot, right? So there's no one solution that's going to get us through, that's going to solve all our problems. But there's a lot of solutions, a lot of tools in the toolbox, and so you have to use those kind of across the landscape. And I think in every situation, a systems approach, it doesn't just consider what's going on in the field, but it considers impacts to watershed scale too. And whether we're talking about carbon, whether we're talking about water quantity, whether we're talking about water quality, a lot of times we see these as we see economics and environment as competing, but I think there's really opportunities to find mutually beneficial solutions. So end of the day, I'm biased, but of course I say that conservation is worth it because we can solve a lot of problems that we haven't thought about. If we think creatively in the field, we can solve problems at the watershed scale too. So contact information, podcast, if you want to learn more about conservation drainage, you can follow me on Twitter post or tweet lots of selfies from the field, and then I'll hand it back over for the CCA information. Be sure to email Elena, and then grab this. Leave it up for about 10 more seconds.
Yeah, if you could send me the CCA information, elenaw@iastate.edu, ALENAW, by 5 today. And then, yeah, our presentation next week is Sometimes the Shield is Not Enough with Sarah Noggle from The Ohio State University. And we already have some questions coming in, but if you have more questions, feel free to go ahead and send them in the chat. First question, though, is relating to the cover crops increasing their bulk density. It was mentioned that there wasn't good cover crop establishment and there was extra passes through the field causing compaction. Does cover crop usage usually or always result in extra passage?
Yeah, that's a good question. And I will, full disclaimer, that's kind of a working hypothesis. So we haven't, I guess, fully vetted that, but that's so the extra passes I was referring to, that would be the result of the planting. So if you're drilling in cover crops in the fall and then the burn down. And so it's not necessarily that they would be, it depends on the system, right? If you're doing fall tillage or if you're doing any type of fall fertilizer application, those could potentially, tillage, not really, but you could potentially couple the planting, the drilling with some other type of fall, field operation. And then again, on the spring, if you're doing other practices, maybe there's an opportunity to get in there to burn it down. And if you have winter kill cover crops, well, then that's not an issue. But if you have something over winters that is, if you have a hardy rye that's really going gangbusters, well, you're going to need to get in there and take it out. But I think to me, it just added a little nuance to the conventional wisdom that, for cover crops to be effective, we needed them to grow more, and we just didn't see that growth. And so we didn't necessarily get as much of the benefit as we would hope with some of the added, I guess, downside.
Okay, another question. Did you have any issues with getting accurate bulk density measurements? And was there any compacting of the soil when taking the deep samples? And with that, what was the probe diameter that you used?
Very good questions. So I think, and that's always a struggle, right? Or it's always a consideration, I should say, making sure that the sample that you're collecting and the measurement you're taking is representative of what's actually happening and not a symptom of the data collection method, right? So we did take pretty good care that if there was, you can watch as you put the core down, you can see if the soil inside it stays put, or once you get down lower, if it pushes down too. So we did take quite a bit of care in making sure that the cores we were collecting were well done, I guess. And so if it did compact, then we'd pull it out, ditch the core and then take another one. And then the diameter, I don't remember off the top of my head, somewhere between 2 and 3 inches, I think. Probably 3 inches, I think.
All right. And then someone just wanted to make sure, they didn't know if you had already said it, but how long were the cover crops and rotations used to show a change in bulk density?
Yeah, so the rotations went in 1991. So very well established. The cover crops were just started in 2014. So when we started, the first round of samples, they would have been in 6 years, and then the last round, 8 years. So 6 to 8 years establishment.
All right. Another question. Have you monitored water table rise in tiled fields as a function of rainfall amount? And any insights from that?
Water table rise in tiled fields, a function of rainfall. We haven't looked at that directly. Some of the work that was done when I was just getting started in South Dakota was looking at controlled drainage. And so water table depths were measured with that. I don't think that work has looked at, variability due to precipitation, though. We have seen, there's a study that was done by USGS, Galen Hugestrat as the lead on that, I think, looking at stream gauge changes and, what that's a function of, excuse me. And one of them is precipitation, but it's not the only factor, right? Like the differences in precipitation accounted for some amount of the change in gauging level, but there was also other factors that influence that. So you could check that report out, USGS, Google Galen Hugestrat.
All right. Another question is, how were the background concentrations of nitrate determined?
Yeah, so my comment that our background in South Dakota is between a 0.5 and 1.5. So that is looking at a lot of, we have a pretty extensive sampling regime in South Dakota that's done by East Dakota Water Development District, done by the state, and all that data is available. There's a portal. It's actually a really nice resource if you're in South Dakota or interested in water quality in South Dakota. But that's been that's not a research observation. I would say that's been my anecdotal observations of kind of reaches that are lesser influenced by any anthropogenic activity. So whether that's agriculture or urban or point sources, whatever the case would be. So yeah, I wouldn't necessarily, I could be corrected on that for sure, but that's kind of what I've seen from a lot of the data that's been collected by those groups.
Okay, a couple more questions. Did you do grid sampling for the soil tests?
So we did not. What we did was, and so that was in plots. And so, you're kind of in a smaller area anyways. But basically where we had the soil moisture probe, we would do within, I think, a 3 meter radius of that, 2 or 3 meter radius of that. And then we were, consistent year to year on kind of that 2 to 3 meter radius. We did do some replication in terms of sample collection. So where we would, each year we would do some replication on terms of how many samples were collected that got composited, that got analyzed. So.
All right. And then the last question I have is, what trend did your biological analysis show in terms of like fungi and bacteria ratio, C and N ratio, Haney test?
Yeah. I don't know yet, to be honest. We haven't really been able to, just haven't had the bandwidth to get through all that data yet. So, to be determined, I guess. Sorry for a non-answer on that one. Because I'm fascinated in the answer to that too, but.
All right. Well, perfect. That is all the questions that I have. Thank you so much, Dr. McMaine, for presenting today. and for rapping. That was very fantastic as well. You can join us next week here, same time, for a presentation from Sarah Noggle. And so thanks, everyone.